Hi everyone, welcome back to this video series on cryptocurrency, the Coinbase transaction. The first transaction on any block is a special transaction called a Coinbase transaction. The transaction is constructed by Jing's node and contains his reward for the mining effort. Jing's node creates the Coinbase transaction as a payment to his own wallet. Pay Jing's address 25.09094928 Bitcoin. The total amount of reward that Jing collects for mining a block is the sum of the Coinbase reward 25 new Bitcoin and the transaction fee 0.09094928 from all the transactions included in the block as shown in example 10.4. Unlike regular transactions, the Coinbase transaction does not consume spend UTXO as inputs. Instead, it has only one input called the Coinbase, which creates Bitcoin from nothing. The Coinbase transaction has one output payable to the miner's own Bitcoin address. The output of the Coinbase transaction sends the value of 25.09094928 Bitcoin to the Bitcoin address. In this case, it is 1MXTKE EP2PM ZE5TUZ1HAV3YTKUTGH1N. The Coinbase reward and fees. To construct the Coinbase transaction, Jing's node first calculates the total amount of transaction fees by adding all the inputs and outputs of the 418 transactions that were added to the block. The fees calculated as total fees equals some inputs minus some outputs. In block 277316, the total transaction fees are 0.09094928 Bitcoin. Next, Jing's node calculates the correct reward for the new block. The reward is calculated based on the block height starting at 50 Bitcoin per block and reduced by half every 210.000 blocks. Because this block is at height 277316, the correct reward is 25 Bitcoin. The calculation can be seen in function get block subsidy in the Bitcoin core client as shown in example 10.5. The initial subsidy is calculated in Satoshis by multiplying 50 with the coin constant 10000000000 Satoshis. This sets the initial reward end subsidy at 5 billion Satoshis. Next, the function calculates the number of halvings that have occurred by dividing the current block height by the halving interval subsidy halving interval. In the case of 277316, with the halving interval every 210,000 blocks. The result is one halving. The maximum number of halvings allowed is 64. So the code imposes a zero reward, return only the fees if the 64 halvings is exceeded. Next, the function uses the binary right shift operator to divide the reward end subsidy by 2 for each round of halving. In the case of block 277316, this would binary right shift the reward of 5 billion Satoshis once one halving and result in 2.5 billion Satoshis or 25 Bitcoins. The binary right shift operator is used because it is more efficient than multiple repeated divisions. To avoid a potential bug, the shift operation is skipped after 63 halvings and the subsidy is set to 0. Finally, the Coinbase reward end subsidy is added to the transaction fees, end fees, and the sum is returned. Structure of the Coinbase transaction. With these calculations, Jing's node then constructs the Coinbase transaction to pay himself 25.09094925 Bitcoin. As you can see in example 10.4, the Coinbase transaction has a special format. Instead of a transaction input specifying a previous UTXO to spend, it has a Coinbase input. We examined transaction inputs in table 6.2. Let's compare a regular transaction input with a Coinbase transaction input. Table 10.1 shows the structure of a regular transaction, while table 10.2 shows the structure of the Coinbase transactions input. 32 bytes transaction hash, pointer to the transaction containing the UTXO to be spent, 4 bytes output index. The index number of the UTXO to be spent, first one is 0, 19 bytes. Unlocking script length in bytes to follow. Variable unlocking script, a script that fulfills the conditions of the UTXO locking script. 4 bytes sequence number, currently disabled TX replacement feature set to 0xFFFFFFFF. 32 bytes transaction hash, all the bytes set to 0, not a transaction hash reference. 4 bytes output index, all bits are 10xFFFFFFFFF. 19 bytes Coinbase data size, length of the Coinbase data from 2 to 100 bytes. Variable Coinbase data, arbitrary data used for extra nonce and mining tags in V2 blocks must begin with block height. 4 bytes sequence number set to 0xFFFFFFF. In a Coinbase transaction, the first two fields are set to values that do not represent a UTXO reference. Instead of a transaction hash, the first field is filled with 32 bytes, all set to 0. The output index is filled with 4 bytes, all set to 0xFF255 decimal. The unlocking script sig is replaced by Coinbase Data, a data field used by the miners, as we will see next. Coinbase transactions do not have unlocking scripts, aka script sig field. Instead, the field is replaced by Coinbase Data, which must be between 2 and 100 bytes, except for the first few bytes. The rest of the Coinbase data can be used by miners in any way they want. It is arbitrary data. In the Genesis block, for example, Satoshi Nakamoto added the text, the Times 3rd January 2009, Chancellor on brink of second bailout for banks, in the Coinbase data, using it as a proof of data and to convey a message. Currently, miners use the Coinbase data to include extra nonce values and strings identifying the mining pool. The first few bytes of Coinbase used to be arbitrary, but that is no longer the case. As per BIP 34 version 2 blocks with the version field set to 2 must contain the block height index as a script push operation in the beginning of the Coinbase field. In block 277316 we see that the Coinbase example, see example 10.4, which is an unlocking script or script sig field of the transaction input, contains hexadecimal value 03443B0403 858402006 to F503253482F. Let's decode this value. The first byte 03 instructs the script execution engine to push the next 3 bytes onto the script stack. See table B1. The next 3 bytes 0x443B04 are the block height encoded in little endian format, backward least significant byte first. Reverse the order of the bytes and the result is format backward least significant byte first. Reverse the order of the bytes and the result is X043B44, which is 277316 in decimal. Next few hexadecimal digits 0385840206 are used to encode the extra nonce. See the extra nonce section, page 249, or random value used to find a suitable proof of work solution. The final part of the Coinbase data 2F503253482F in the ASCII encoded string P2SH, which indicates that the mining node that mined the block supports the P2SH improvement defined in BIP 16. The introduction of the P2SH capability requiring signaling by miners to endorse either BIP 16 or BIP 17. Those endorsing the BIP 16 implementation were to include P2SH in their Coinbase data. Those endorsing the BIP 17 implementation of P2SH were to include the string P2SH CHV in their Coinbase data. The BIP 16 was elected as the winner, and many miners continued including the string P2SH in their Coinbase to indicate support for this feature. Example 10.6 uses the LibitCoin library introduced in alternative clients, libraries and toolkits to extract the Coinbase data from the Genesis block, displaying Satoshi's message. Note that the LibCoin library contains a static copy of the Genesis block, so the example code can retrieve the Genesis block directly from the library. So I'm going to leave it here today for this video. Just before I go, example 10.16, extraction from the Coinbase data from the Genesis block. So here's the output from that. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.